Hi, in this second presentation I will explain how the test coprocessor control path works, and this is indeed an explanation of how to design each test command. After watching this presentation you shall be able to explain in detail the operation of the control path that is proposed for this coprocessor architecture, and you shall be able to design the ASMD shards for the remaining test commands. Now the references are again the same that were presented for the coursework specification, that is to say the Circuits and Systems paper and the microprogrammed state machine design book. This is the proposed architecture for our microprogrammed control path. The basic idea consists of having a microprogram memory that contains as many sections as the number of test commands that are to be supported. Each section will start in an address that corresponds to the test command opcode. For example, the reset command section may take up the first positions of the microprogram memory, followed by the TMS commands, etc. Whenever a new test command opcode shows up at the shared memory RAM content outputs, it will be loaded into the bank register block to mark the initial address of the corresponding microprogram memory section. Then the remaining part of this architecture will increment the microprogram memory address through the ASMD state register block and its incrementer block as we progress through the command ASMD chart states. Notice that the microprogram memory address will be incremented by 1 for each system clock cycle, provided that the load control signal for this multiplexer remains at 0, so this loop will be in place. The encoder on the left is responsible for taking the micro-operation code coming from the microprogram micro-op field and defining what the control path architecture must do for each new test clock, for each new system clock cycle. If we want to jump to any other microprogram memory positions, for example, we can use the new address field and set the multiplexer load control input to 1, in which case at the next system clock cycle the ASMD state register will load the new microprogram memory address offset. And of course for each ASMD state, that is to say for each microprogram memory position, the control outputs field in the microprogram memory defines what is to take place in the regular sequential circuits comprised in the data path. But let's look into a specific example to explain how this architecture works. We will consider the MTCK, or multiple test clock command for this purpose, because this is an intermediate complexity command. The reset and TMS commands are simpler than this one. Everything begins with the external start order, which must initialize the control path architecture. This means that we must reset the shared memory address counter, we must load the bank register, and we must reset the ASMD state register that defines the microprogram memory address offset within each section. Let's see how this happens. So the operating conditions set up by the external start order are represented as shown in this slide. Notice that the reset signal for the shared memory address counter must be asynchronous, and I repeat, it must be asynchronous, because we must have the first test command opcode already available in the RAM content bus when we load the bank register to select the corresponding initial position in the microprogram memory section, and this will take place at the next rising edge of the system clock cycle. So this RAM content bus must be updated before that moment. Upon the next clock cycle, what will happen is that the bank register will be loaded with the MTCK opcode, and the ASMD state register outputs will be all 0. And this means that we are now in the first position of the microprogram memory corresponding to the MTCK section. And we will be ready to start the execution of this test command. This is where we are in the ASMD chart of the MTCK command, which is supposed to increment the shared memory address, or in this case a RAM, so that we can get the required number of TCK pulses to be loaded into the current bits counter. Let's look to what happens in the control path during this system clock cycle when we are in the MTCK 0 state. The increment RAM and continue micro operation coming from the microprogram memory position sets up these conditions. Because we will continue to the next microprogram memory position, the MUX multiplexer load input is set to 0, and therefore the ASMD state register will go from 0 to 1 in the next clock cycle. And likewise, the increment RAM address is active, so the RAM content bus will now show the required number of TCK pulses. However, the bank register, as you see here, remains with the MTCK opcode, since the number of TCK pulses value is needed for the data path, not for the control path. And we will move on to the MTCK1 state. In MTCK1, we will load the data path current bits counter with the number of TCK pulses and continue to the following MTCK2 state. Let's look at the control path operating conditions for this code, for this case. Since the micro operation is now continue, the multiplexer load control input remains at 0, and the ASMD state register will go from 1 to 2 in the next system clock cycle. This means that we will go from state 1 to state 2, where we will check for the logic conditions, which we called condition A. And this condition asks, is the current bits counter equal to 1? Let's assume that our command was MTCK1, so there was only one TCK pulse required, so that we don't take too long in this explanation. In this case, we must move from MTCK2 to MTCK3. Let's see how this happens in the control path. The branch if condition not A micro operation defines that the multiplexer load control input will be 0 in this case, because the condition is true, otherwise it would be 1 and we would jump to state 2 again, to state 6, sorry. This means that the ASMD state register will go from 2 to 3, and we will go from state MTCK2 to MTCK3 as required. In this new state, we set the board test clock pin to 1 and continue to MTCK4. Let's see what happens in the control path. The multiplexer load control input is set to 0, as always in the case of the continue micro operations. Notice that the board TCK pin is set to 1 as required in this state, and that the next value of the ASMD state register will be 4. This takes us from state MTCK3 to state MTCK4, where we will start to prepare the execution of the new test command. Now in MTCK4 we need to increment the shared memory address and continue to MTCK5. Let's see how this takes place. The microoperation is now increment RAM address and continue, the RAM being our shared memory. And this microoperation defines the operating conditions that are shown in this slide. At the next system clock cycle, the shared memory will be incremented, so the next command opcode will show at the RAM content outputs, and we will advance to the following position in the microprogram memory section, which corresponds to state MTCK5. Notice that the next test command is already available and ready to be loaded into the bank register, and this will actually take place in state MTCK5, which leaves everything ready for the next test command to be executed. What is left to do now is simply to load the bank register with the new test command opcode and to reset the ASMD state register. Let's see how this happens. The operating conditions for the microoperation LRC, or load bank register, reset ASMD state and continue, are shown in this slide. By loading the bank register with the new test command opcode and resetting the ASMD state register, we will continue to the first microprogram memory position in the section corresponding to the new test command. The one state that we did not look into, because we only needed to drive one TCK pulse, was MTCK6. Let's see what happens in this state to conclude this presentation. In MTCK6 we need to decrement the current bits counter and to set the board TCK pin to 1. Let's check how this takes place in the control path. These are the operating conditions shown for MTCK6 state. In this case we will not continue to the next position in the microprogram memory, but rather jump back, as you see here, jump back to state 2, MTCK2. For this reason, the multiplexer load control input is now set to 1, and therefore the new address field that will be loaded into the ASMD state register will be the one that corresponds to the position defining state MTCK2. So the value coming from the new address field in the microprogram memory is set to define the offset that will take place from position 6 to position 2. This is 0, 1, 2. The board TCK pin is driven to 1 as required, as you see here. From this point on, we would simply return to state MTCK2 and continue from there as we saw earlier. And this was all about the operation of the proposed microprogrammed control architecture. Please use our course discussion forum if you have any questions. Good luck with your work.